Okay, so in my last talk, I introduced integrability in a classical system. So today, the goal is to motivate what integrability should mean in a quantum setting and to give some examples of integrable systems that we see in practice. So I will start with a brief recap of what we discussed in our last meeting. So a quick recap of classical integrability. The idea behind integrability was that these are dynamical systems in which the dynamics are nice in some sense. And the sense is that we can expect to be able to solve the equations of motion, and the solutions are not chaotic. And kind of the hallmark of integrable systems is the existence of a large number of conserved charges. So for example, in Kepler's problem, which is the problem of a particle moving in inverse square potential or the planetary motion around a star, the conserved charges are the angular momentums. And knowing that these angular momentums are conserved allows one to solve the equations of motion. In case of simple harmonic oscillator, again, we have, well, it's a one-dimensional system, so you only need one conserved charge, and the energy is conserved, so you can also count that as an integrable system, and we of course know that we can solve this problem. There are many more examples like this. So this idea was formalized by Liouville, who said that if we have a classical mechanical system of dimension 2D, by which I mean that the phase space has dimension 2D, 2D dimensional phase space. And if you have D conserved charges, let's call them J1 to JD. So these are functions of the coordinates on our phase space, so position and momentum. And if these conserved charges are in involution, which means that the Poisson bracket of any two of these conserved charges vanishes, then this system is integrable, meaning that you can expect that you can solve the equations of motion of this system. So just a reminder, so conserved charges means that you of course have Hamiltonian as part of the definition of your mechanical system, and all of these charges commute with Hamiltonian, which is the same as saying that their time evolution is trivial. Now, this was kind of easy to understand, but it's very difficult to generalize. And so instead of trying to generalize this notion of integrability, we came up with some somewhat more abstract way of expressing this criteria, which was called the lax formalism. So what it does is that it starts with the assumption that you have two matrix valued functions on your phase space. So let's call them L and M. So this is my phase space. By the way, if anyone has any question or if anything is unclear, the definition of something or the notation of something, just ask, and yeah, I mean, I will clarify and then move on. So they are matrix valued, so I will write them as G, by which I mean there is some kind of Lie algebra, but really you can just think of them as matrices. So for example, if G is GLN, then that's the same as the space of n by n matrices. So it's fine to think of them just as matrices of some dimension n by n. And since these are functions on the phase space, the entries of these matrices, for example, so if you write L as an n by n matrix, then the entries are going to be functions of position and momentum. So they're functions of Q and P, all of these entries. Okay, so suppose that you have two such matrices, and furthermore that they satisfy the following equation. If the time derivative of one of them is the commutator with the other. So this is a single equation. I don't mean that you also have another equation with M and L swap. That's not the case. Just the time derivative of L is the commutator with M. Now, so on the left-hand side, when we take time derivative of a matrix, we just mean that you take time derivative of each component, and that's it. So this immediately implies the following, that if you define some functions, such as these, so this is the L power of L, nth power of L, and then they take the trace. So this now, notice that is an ordinary function on the phase space, right? Because so L was a matrix, it took some power and then ultimately took a trace, so it's going to be some functions written in terms of these entries. So it's just a function on the phase space, like any observable in your system. And from this equation, it's easy to show that the time derivative of these functions vanish. So this way, you immediately get a set of conserved charges. But recall that in Liouville's characterization of integrable systems, the conserved charges also have to be in involution. And that's not obvious from here. But we can also argue that that is also true under certain assumption. So let's look at these extra assumptions. To write them down, we need to introduce some notation. So for example, let's call L1 the same matrix L, except now it acts on a somewhat larger space. So any n by n matrix, so for simplicity, let's say that L is an n by n matrix. So then it acts on Rn. It's a map from Rn to Rn. Now imagine.
I have a question.
Yes.
But this n is not the same n as On, right?
No. Oh,
it's confusing.
Yeah, sorry. That's a good point. Sorry.
So, yeah, you can call it M by M maybe.
Yeah. Let me just change this notation. Let's say I. Yeah, that's right. So this n is completely different. Right. So now imagine a somewhat bigger vector space, which is a tensor product of Rn with Rn, and a map from this space to itself. And then this operator acts on this space, right? So L acts on Rn, and in the second copy of Rn, we just have the identity operator. And similarly, you can define L2 to be identity times L. So this is 2. So this operator acts non-trivially on the second factor and trivially on the first factor. All right. Then assume that there exists a different operator, R12, which acts non-trivially on both factors. Okay. Then we shall be able to prove involution if the following equation holds. Okay, so on the left-hand side, we have the Poisson bracket. And on the right-hand side, we just have commutator with respect to matrix multiplication. By the Poisson bracket, we simply mean that, so take L1, A, B, L2, B, C, sum over B. And then this will be the AC component of this matrix. And here you get a matrix because you're just using matrix multiplication. So this is the meaning of, this is how you interpret this equation. Now, the claim is that if you have a matrix such as this, and if L satisfies this equation, then all these charges that we already know to be conserved are also in involution. Then if you can find this matrix of sufficiently large dimension, because by large dimension, I mean if n can be sufficiently large, then you have a completely integrable system. Now, what is the significance of n being large? So notice that if L is an n by n matrix, then you can only take n independent traces, right? So you can take trace of L0, L2, dot, 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 Ln minus 1, I think, or maybe Ln. Okay, then, well, L0 is 1, it doesn't matter. Right, so you can take these traces, but if you take trace of something, say Ln plus 1, then this trace can be written as a function of these traces. So for an n by n matrix, you only have n independent traces. So if you're working on a phase space of dimension 2D, then you want at least d conserved charges. So n should be at least d. Now, if you can find such matrices L and M, from which you construct these d conserved charges, and then furthermore, if you can find these R matrix, which satisfies this equation, then you can find d conserved charges in involution, and that gives you a Liouville integrable system. Okay, so this was an alternative characterization of the same integrable system that Liouville characterized. The benefit of this formalism is that this can be generalized both to field theories and in quantum cases, which we shall look at now. Okay, so before we do that, are there any questions about this formulation?
So, but I have a very trivial question. So in the Liouville formalism, J1, J2, those were conserved charges, right? Like charges.
Yes. Mm-hmm.
So what should I think about this L1 and L2 you are defining? These are also conserved charges, right?
So Lm or L1, L2, they do not have an obviously, they do not have an obvious interpretation as a conserved charge. But if you take the power of L and then a trace, then the functions that you get, these are conserved charges.
Right.
So you can think of them as the J's. So maybe I can even write them as J's.
I see. And what are these LIs? How should I think about them? I have to construct them or something for each individual theory?
These L matrices?
Yes, L or LIs. Yeah, these things.
Well, so Li is just L put in some factor. So
right.
There's nothing non-trivial about L1 if you know L.
Mm-hmm.
But there is no prescription for how you can construct L given just a Hamiltonian and the phase space. This is completely, this is research material that if I give you some random dynamical system, even to figure out whether such an L exists is a challenge. There's no general prescription for doing that. Okay. But if you can find such an L and such an R, then you know that you have an integrable system.
So can I ask a question? Sorry, if
yes.
So you said that if I have an n-dimensional matrix,
yes,
then I can only have independent traces. That is,
Right.
I can take the trace of the matrix or the trace of the square of the matrix up to trace of the nth power of the matrix, right?
That's right. Yes.
And if there are, if I take trace of something with a higher power, then that should be expressible in terms of the trace of the other
Lower power,
matrices.
yes.
So is that a theorem from linear algebra?
Yeah. Yes.
Okay.
Yeah, something to do with the determinant of the matrix satisfying some weird equation. Well, the characteristic equation.
Okay, thank you.
Right.
Bhaiya,
So, yes.
So the J's that you have defined as the trace of L of I, L to the power
Yes.
I, like, are these, will you interpret this J as my global global charge of the system, or they are
Yes.
or the local observables that you are?
No, they're global.
They are global.
Yeah.
Okay. And okay.
No, so,
and why you are
what
defining,
definition of
yeah.
what definition of local charge do you have in mind?
I was thinking of that. These are like you know, like as these L are a function of phase, the phase space, right? So I was thinking that these J's are actually local observables or local conserved charge at each point in the phase space.
No, yeah, that's true. That's true. So what I meant by global is that they're not related to gate symmetries. That's what I meant. They're related to global symmetries. But yes, they are functions on phase space. So they are going to be functions of your position and momentum.
Oh, but they're the global charge of my system. I see.
Yeah.
Okay. And another question is that why, you know, you have defined, you have said that you need, you know, you have these two matrix L and M. Then why we need these L1 and L2? I mean, like, why you have decomposed the system in L cross 1, L cross identity, and L2?
That's simply to be able to write down this equation. So because R is a matrix that acts non-trivially on two factors of Rn. And so if I define these matrices, then I can write down these equations. But it's not, strictly speaking, necessary. I mean, I can also write down these equations without introducing this factorization. But then this equation will look a bit more complicated. So for now, you can just think of this as some useful linear algebra trick so that this equation takes a simple form.
I'm sorry, I also have a question.
Sure.
So R12 and R21 are just, I mean, they swap the action on the two RNs?
That, in some cases, yes. Well, actually, I mean, in most cases, that will be true. So R12 will be negative of R21, but a priori, it's not necessary.
Negative of R21, or just their action on the two RNs are swapped?
You mean like a permutation?
I mean, R21 is a map from Rn times Rn to Rn times Rn, right?
Yes.
And I mean, I'm not sure about the indices there, 1 and 2. And 2, 1.
Oh, yeah, what? I mean, I put 1 and 2 just as a reminder that this is a matrix that acts on two products of Rn.
Okay, then what does it mean by R21? Is it a
So
different operator, or?
I mean, I haven't defined R21. Oh, even here. Oh, sorry. Here, okay, you're right. So here I just meant that actually, yeah, so what I had in mind is R21 is equal to minus R12, but that may not always be necessary. Let's see if there's something general. Oh, sorry. Okay, yeah, I can define it this way. So R21, you can say is, so take a permutation operator that acts on the space. So a permutation operator means that if you take a vector from here and the vector from here, the permutation operator will give you it will just solve the two vectors.
Right, yeah.
So take the permutation operator and do the conjugation. So let's say pi is the permutation operator. So R21 is this thing.
Okay. Now it makes sense.
Basically, you're saying the R1 is these are for the first slot. The first slot is for the first RN, and the second is for the second RN. And when you do R21, the second RN comes first. And is something like that, right?
Yes.
Can you please explain or give you a glimpse that why? Why these R12? Why you bring them?
It's very difficult to interpret in the classical system, but when I go to a quantum mechanical system, this thing will become much more natural. And yeah, I will try to explain it then. And so far, just think of this as some kind of mathematical trick.
Okay.
Yeah, interestingly, these things become simpler to understand in the quantum mechanical setting rather than in the classical setting. Okay, but before we go there, we need to generalize a little bit more. So let me now talk about integrable 2D systems. Yeah, so once we have established this mechanism, there are different ways that we can generalize. So one way is that we can talk about, so far the kind of systems that we have talked about is basically a particle moving in some space, because you had a phase space with coordinates and momentum, and you can think of those coordinates as coordinates of some particle. So what is a particle moving in some space? The trajectory of the particle is some line in some target space, right? There's some particle moving. Now, one way to look at the system is that you can think of the system as a 0 plus 1 dimensional system. So what does it mean? It means that you think of this as a quantum field theory, but from the perspective of the world line. So on the world line, you only have a time direction, and there's no spatial direction. So you have 0 spatial direction and 1 time direction. So that's why it's a 0 plus 1 day system. But you can now generalize this to a 1 plus 1 day system. So you replace the world line with some world trade. So now you have some kind of strings moving in some target space. Okay. So let's look at that situation. So what do we have to do here to get to that generalization? Actually, not much, because we have whatever phase space we have. We don't have to worry too much about what the phase space actually looks like. What we have to introduce is that, so here we have the time coordinate, but we now need to introduce a spatial coordinate, right? So here we just have the time coordinate. This is the time coordinate. So we still have the time coordinate, but we want to also introduce a space coordinate. Let's call it X. So then I claim the following, that the generalization of this equation, when we have also a spatial coordinate, is the following equation. So once again, you have the matrices L and M, which are matrices, matrix valued functions on your phase space, whatever the phase space may be. And they have to satisfy the following equation. Okay, so it's a simple generalization. Basically, I have just added this term. So just to this thing, you just add del M del X, and that's it. So I claim that this is my new Lax equation. Yeah, it's hard to motivate why this is a correct equation. So let me just claim the results. And as I was saying, that I will interpret these equations once I go to the quantum system. Okay, so I will make one more generalization, which is that I will assume my Lax matrices and R matrices depend on an auxiliary variable. And I will use the symbol U for this auxiliary variable. Now, what it means is that, so by definition, L is a function of position now. By position, I mean this new position coordinate, not position in the phase space. X, t, and your phase space variables, q and p, right? And so is m, and so is r. But I am adding to this description yet another variable. This variable has absolutely no interpretation as a coordinate in your physical system. What this variable tells you is that you have not a single lax pair and an R matrix. Rather, you have a family of lax pair and an R matrix, one for each choice of u, whatever u is. Okay. So this may seem like a stronger condition than what we originally had, because previously we just said that if you find a lax pair, by the way, so the lax pair refers to this L and M, and R is the R matrix. So previously our claim was that if you have a lax pair and an R matrix, you have an integrable system. Now I am saying that I'm not looking at this kind of general integrable systems, but I'm looking at the kind of integrable systems where I not only have one lax pair and an R matrix, but a family of lax pair and R matrices parameterized by u. Yeah, so once again, this may seem like overly constraining. However, most of the physical systems that we encounter fall into this category. So for now, I'm just going to assume that this is the case. And going to discuss examples where this is true.
Does u have to be continuous or discrete?
I'm going to assume that u is continuous.
Is it always the case, or it can be like discrete?
If it's discrete, then it doesn't really do anything. Meaning that the reason that we introduce this u, as you will see, is that it will make some computations easier because we'll expand things in u and look at the coefficients. Now, if u is discrete, you cannot do that. So it doesn't simplify the problem.
Okay.
Sorry, Bear. So why you are going to from wall line to wall sheet perspective? Where's that?
Because, well, in one way of thinking, you can just say that, well, it's the obvious generalization. You had 0 plus one-dimensional integrable systems, but what about integrable quantum field theories or integrable classical field theories? So there you need to introduce some extra coordinates. But the reason that I am adding this extra coordinate is that I want to talk about integrable spin chains. Now, integrable spin chains can be motivated in different ways. The easiest way to do so is that they model simple magnets. Now, integrable spin, the continuum limits of integrable spin chains are integrable 2D field theories. And to introduce that, I'm introducing this extra coordinate. Does that answer your question?
Yeah. So finally, you're gonna talk about like let's say two-dimensional quantum field theory or something like that. That's why. Okay.
Well, I will talk about the discrete version of that, which is the spin chain.
Okay. Okay. Yeah.
Okay.
So Bhaiya, so just to be clear, so QP is the ambient space-time dimension in which this is world is moving. So it
Yes.
is 2D, but it is moving in this ambient space-time dimension.
That's right.
Which has
Yes.
Okay.
So these are phase space coordinates. Or yeah, as you were saying, that ambient space. They're also called target space. And these are my 2D worldsheet coordinates. All right. Now, to show how we can get integrable charges from this, define the following matrix, which is I'm going to keep the U dependence explicit and hide all dependence on the other variables. So this is basically Let me explain what this is. So this L is the same as this L. So here I'm hiding the dependence on the phase space coordinates. And I'm integrating over the X coordinate. S minus and S plus are just two arbitrary values that I have chosen for this integration. And strictly speaking, this should be path ordered in that when you have probably seen this kind of integrations in QFT courses where when you expand this thing, you should, I mean, since this is matrix and they're non-commutative, you have to choose some kind of ordering of how you put different matrices, right? Because if you expand this, you'll find L, 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 and then you have to choose some kind of ordering between these L's. The idea is that you order them the way it is ordered according to position. So you go from S minus to S plus and choose some ordering of matrices. Okay, that's a technical point, not too important. The main point is that you can define this kind of matrix. So this matrix no longer depends on this X coordinate, right? But it does depend on T. So maybe I will write T. And this is called a monodromy matrix. Okay. And you can see that this is similar to how you construct monodromy in a gauge theory. So if you had some kind of connection, you would integrate the connection over a line, and that will give you a monodromy of the connection on that line. That's where this name comes from. Now, this matrix has some nice properties. For example, if you take the time derivative of this thing, what you find is that M evaluated at S plus, T minus T, M evaluated at S minus. So this M is part of the Lax pair. And of course, I'm assuming that this L and M satisfy the Lax equation. That's how you get these M's. So this is M evaluated at S plus. So M is, of course, a function of X, T, and etc. So you get this equation. Now, if you choose, for simplicity, let's say that our X direction is periodic, okay? And I take S plus and S minus to be the same, meaning that this integration is on a closed curve. So then this equation becomes the following. So, I mean, if S plus and S minus are the same, then this is a commutator, right? Let's call it 0. I mean, I'm saying S plus equals S minus equals 0. Then you find this equation. Yeah, I should keep the U dependence explicit because that's going to be useful. Okay. This equation now looks exactly like this equation. So in going from one-dimensional field theory to two-dimensional field theory, we modified our Lax equation somewhat, but we find that we can still define an operator in terms of our L operator that satisfies the same equation as the zero-dimensional field theory version. So then we can construct the conserved charges from this T in exactly the same way as we did from this L. Right? And then because the time derivative is a commutator, the traces are going to vanish. But due to the presence of this U matrix, we can kind of simplify this. Basically, instead of taking powers of T and then taking the trace, we can simply say the following, that just take the trace of T. What should I call it? Let's still call it T, but some kind of fancy. Is that a T or an F? Maybe that's no. Yeah, okay. Let's say this is a T.
Nafiz, I think we cannot hear you. Nafiz, I cannot hear you. Yeah, you should give the join audio, I think.
Yeah, I think you have to unmute yourself.
Nafiz, you have to unmute yourself.
Hello.
Yeah.
Yes.
Well, yeah.
Perfect.
So I was connected from. I mean, I was connected to audio from my computer. I think something went wrong in my computer.
Yeah,
So
it's
now I'm
always
connected
happened.
from my tablet.
Yeah. Okay, no problem.
Can you hear me now, everyone?
Yeah.
Yeah.
Okay. Right. So I was saying that if you take trace of the monodromy matrix and define this matrix, which is called the transfer matrix, then the transfer matrix is conserved simply because you are taking trace here and you're taking trace here, and trace of a commutator is 0. Okay, that's fine. Now, since this is a function of u, you can expand this thing as a power series in u. So you can write it as something like this: u to the power I sum over I. And this is conserved for any value of u, meaning that all these coefficients are individually conserved, right? So this way you get a lot of conserved charges. Okay, that's fine. We also had a lot of conserved charges from this equation, right? These were the conserved charges. But in order to find integrability, we also have to show that these conserved charges are in involution. And so previously, in order to argue for involution, we had to introduce the R matrix and some equation. And here again, we have to do the same. Now, this part, okay, the equation looks very similar. So let me just write down the equation first. So once again, we introduce these L1s and L2s. They are now functions of x, t, u, in addition to the phase space coordinates, which I'm not writing down.
Yeah. Hello.
Yes. Yes.
So yeah. So like, how do you? I mean, like, how do you can say that these j's can be expanded in powers of u? I mean, like, can this ji like something like like 1 over like 1 over x step function, and in that case, do you have this convergent series? I mean, like, is it something you are assuming, or
that I can expand this in this way?
Right.
It doesn't have to be convergent. So you can think of this as an asymptotic expansion. I mean, even if this series does not converge. So yeah, you can think of this as an asymptotic expansion.
Is it something like the operator product expansion?
Well, I mean, in the sense that operator product expansions are also asymptotic in general, yes. Although I'm not taking an operator product.
Okay. You are just simply expanding it in partial use.
Right. Okay. So now I'm writing down the generalization of these equations. We have bracket with L1, L2, and something written in terms of the R matrix and L. So I'm going to write down something similar. Again, you have to have some kind of R matrix. Okay, so let me explain this a little bit. So on the left-hand side, again, we have the bracket of L1 and L2. They are evaluated at the same time, but at different worldsheet positions. And also, I'm using two different values of the spectral parameter. Oh, sorry. So this auxiliary variable that I'm using, this is often called the spectral parameter. So I will be referring to it as the spectral parameter. And the R matrix also depends on the spectral parameters. So basically, so remember that these matrices act on two vector spaces in tensor product. So L1 acts here, L2 acts here. And this U and U prime, you imagine them as being associated to either this factor or this factor. And the R matrix, which acts on this entire space, has to depend on the difference between these two spectral parameters. And then I have basically the same thing as I did here. So the bracket of R matrix with L1 and L2, but I have changed the sign and added them up, assuming that this R matrix satisfies something like this. So I'm assuming that once I conjugate with the permutation matrix, I just get the negative of the original R matrix. Okay. But don't worry too much about the details of this equation. I will use a simple form of this equation later. For completion, I'm writing down what the necessary conditions are for these conserved charges to be in involution. And the necessary condition is that, well, actually it's not clear if this is necessary, but it is sufficient. The sufficient condition is that if you can find such an R matrix that satisfies these equations with your lax operator, then all these conserved charges are in involution, as it was in the 0+1 dimensional case. And there's a factor of the delta function as well. That depends on the difference between these two position coordinates. Okay. So for now, let's just say that I'm saying that this is a sufficient condition to find an integrable system. So one consequence of this equation for the Poisson bracket of the transfer matrices. So recall that the transfer matrix was the trace of the monodromy matrix T, where T was this path ordered exponential of our lax operator. So from here, you can derive the following relation between the Poisson brackets of the transfer matrix, the monodromy matrix, sorry. So T1, U, okay. Now, this is an important equation. So let me quickly recap how we came to this equation. We basically said that we have some phase space, the phase space of our two-dimensional field theory, whatever that phase space is. We're not too concerned about the details. And we have two matrix valued functions on this phase space. And they're also functions of position and momentum. And they satisfy this Lax equation. Right? So this is the Lax equation. Given that is the case, we further assume that we have not just a single pair of Lax operators, but a family of Lax operators parameterized by U. They all satisfy the Lax equation. Then we constructed a monodromy matrix by taking a path ordered exponential of our Lax operator. Then we showed that if we take the trace of the monodromy matrix, we find the transfer matrix whose Fourier coefficients, let's call them Fourier coefficients, why not? Or something like that, which is what we get by expanding the transfer matrix in the variable, which is the spectral parameter. So these coefficients, they are conserved. So these are our conserved charges. Furthermore, these conserved charges are in involution if our Lax matrix satisfies this equation involving the R matrix. And from this, we found the Poisson bracket of the matrix components of the monodromy matrix. Now, so what information does this equation contain? So the coefficient of this monodromy matrix, these are function of our phase space variables. So that's how you compute this Poisson bracket, because we know how to, presumably we know how to compute a Poisson bracket of functions of variables of our phase space. And these are also matrix valued, and this is another matrix valued operator, and this is just the matrix commutator, right? So this tells you how, this basically has the information of Poisson bracket on your phase space. Okay, so knowing this equation is basically telling you that you have some classical integrable systems, and this classical integrable system can be just a particle moving in some space, or a string moving in some space, or even something higher dimensional, although we have not really discussed that. So basically, this is how you present an integrable classical field theory, regardless of dimension, in terms of some matrix called the monodromy matrix and an R matrix. Now, so starting from here, I'm going to talk about quantization. And in some sense, the quantum picture is conceptually more satisfying, because so here you may think that we have to do a lot of ad hoc things to get to this equation, and that's true. But it will make more sense in the quantum case. But before I talk about the quantum case, are there any questions regarding this equation?
So about this spectral parameter, does it has to do anything with spectrum of the operator T1, T2, or R, or it's just a name?
Not in any direct sense, no. Yeah, so it's really just a name.
Okay, and
yeah.
Okay, so one question more. So, so you considered this x coordinate compactified, and is it essential that you have to consider it, or you can relax it?
No, you can relax it, but then you have to choose some boundary conditions at the end for the equations to work.
Oh, okay. Okay, thank you.
So I have a question.
So, yeah.
Sorry. Okay, Jawad, go ahead.
Okay. So like, will you relate this parameter U to, to some gauge parameter of your system? Will you? No. Okay, it's just an parameter. Okay.
Yeah. So far, it has absolutely no interpretation. Just some auxiliary variable.
Okay, so my question is, if I look at the transfer matrix, it looks like the Wilson loop, right?
Yes.
And so
the monodromy matrix.
The monodromy matrix, right? So that gives me the conserved point. The transfer matrix.
Yeah, maybe you said that the trace of this thing is the Wilson loop.
The Wilson loop, right? Yeah. So my question is, I'm confused with the vector spaces that are there. So you have the worldsheet.
Yes.
And you have the phase space.
Yes.
And you have, but those T matrices or the L matrices that are acting on some vector space, which is different, right? Which is of
which
size
is completely
N.
different. Yes. Yes.
And then can you go down a little bit when you wrote that VU in blue? So is this parameter U a parameter of this vector space?
You can say that, yes. So this is associated to this auxiliary space on which your lax operators or these things act.
I see.
Yeah, but I mean, both of these are equally auxiliary at the moment.
And what are the dimensions of these vector space? So this depends on the size of the lax matrices.
Yeah,
right?
yeah, that's right. If your lax operator is n by n, then these are Cn or Rn.
Right. Okay. Okay. Thanks.
All right. So now let's discuss quantization. So let's recall how we quantize a classical system. We have, so in classical mechanics, we have functions on our phase space, and those functions have Poisson brackets. And in quantum mechanics, we promote those functions to be some operators that act on some Hilbert space, and we promote those Poisson brackets to commutator brackets of those Hilbert space operators in some limit where the quantization parameter h bar goes to 0, right? So we will do exactly the same thing, except that we will focus on the particular functions on phase space that appear as coefficients of these matrices. Okay, so these are the, recall that these are the monodromy matrices, right? So T1, well, if I just write T, the 1 is pointless. So this is some kind of matrix that acts on some auxiliary space, these V's, and they have entries say T11, which depends on U, but also on the phase space coordinates, right? So 1 to U and so on and so on and so forth. And this equation tells you how to take the Poisson brackets of these things, assuming you know what the R matrix looks like. So our basic idea now is that we shall introduce a Hilbert space. Right? And we shall promote these coefficients to operators on this Hilbert space. I mean, you cannot say that this becomes an operator in the Hilbert space, right? Because this is not just a simple function on a phase space. These are matrix valued functions on the phase space. So we will have to deal with that matrix at some point. But for now, these are just ordinary functions on a phase space, and we can simply promote them to be operators on a Hilbert space. Operators that depend on an auxiliary variable U, but that's fine. And the brackets between these operators, well, they are going to be promoted version of the Poisson brackets, okay? So there will be some brackets of, okay, actually, before writing to the brackets, so let's deal with this matrix part. So what happens when we promote these to operators on Hilbert space, okay? So let's call that quantization. And let's say that when we promote a function of phase space to an operator on Hilbert space, we put a hat over it, right? So T11 hat U, T12 hat U, and so on. Okay, now these are acting on the Hilbert space, that's fine. But what about the full thing, the full TU? What is this acting on? The answer is that TU acts on this Hilbert space tensored with this auxiliary space that we have, right? And why is that the case? Because imagine an element from this tensor product space. So what does this element look like? So you can write such an element as a column matrix where each entry corresponds to a basis vector of V. But instead of having a complex number as a coefficient, you have an element of H as a coefficient. So you have some kind of ket, let's say alpha, beta, and so on. Okay, so what I'm saying is that you can write an element of this space as something like this. And then if you take a matrix that looks like this, then when you do the matrix multiplication, so you will multiply these things with these things, and these being operators on H will act nicely on these components. And you will end up with another column vector where the entries are elements in H. Now, is there any confusion about this claim? Is it clear that if the entries of the matrix belong to the space of operators on H, then the full matrix acts on H tensor V? Is that statement clear?
No, it's not clear to me, because I expect like H tensor with H of all the entries, like n by n, because so T1 maps H to H and T1
That's
to
right.
map H to H. That means I have a map which is a like the whole matrix, like the T that maps. So T1 and T12, does this map to same Hilbert space H?
Yes.
All
yes.
Oh, okay. Then it's clear. Okay.
Oh, okay. Yeah. They all act on the same Hilbert space, and the codomain is the same Hilbert space.
And by Hilbert space, you mean just a L2 space, right?
Yes.
Okay. Okay. Thank you.
Okay.
And I have a question. This V is the tensor product of two V's that we had before?
No, it's a single V.
But it's the two n-dimensional space or the n-dimensional space?
N-dimensional space.
Oh, right. But T was.
I mean, so L was an n by n matrix, right?
Yes.
So this L was an n by n matrix.
Oh, yes.
So
right. Okay.
for the same reason, this is an n by n matrix.
Okay.
So this is going to act on, let's say, Cn, which is what I'm calling V.
Okay.
Okay. So by the general principle of quantization, when we promote functions on phase spaces to operators on Hilbert spaces, our monogery matrix becomes an operator on the Hilbert space tensored with an auxiliary space V. Now, so let's call this quantized version T hat. So now let us look at, so basically what we want to compute is what is the commutator between two of these things located at different spectral values. And this has to be such that if we divide this by H bar and take H bar to 0, we should find the Poisson bracket. And the Poisson bracket being this object. So we know this from whatever classical information we had, and we want to find quantum operators that satisfy this equation, right? Now, well, so we also have to do something to R. So let me now introduce the quantum R matrix. Ij, well, I've been writing this as 1, 2, so let's call it 1, 2. So roughly speaking, up to some constants, this is going to be simply an identity operator, well, tensor identity operator, plus H bar over U minus U prime, and then the classical R matrix. And then you have higher order corrections. Okay. So this is just my definition. Actually, yeah. So let's just say that I'm defining this quantum R matrix, and then you can again show, I'm not going to prove, that the quantized version of this is the following equation. Okay. So as usual, T hat, you at the classical level is just the ordinary thing, plus there can be H bar order corrections. Now the claim is the following. Expand this in H bar, take H bar goes to 0, and you will recover this equation. So the classical counterpart, right, as it should be. So basically, what I'm claiming is that the quantum version of this equation involving the classical Mondrian matrices and the classical R matrices is this equation involving the quantum Mondrian matrices and quantum R matrices. Okay. Actually, I mean, this is just a simple computation. We expand things and take limits, but there's some algebra involved. So let me just say that this is true. And this again is an important equation. It's called the RTT equation for a very obvious reason. Now, so from here you can discuss integrable quantum field theories if you want. But I'm going to focus on something simpler and more specific, which are quantum integrable spin chains. But before doing that, so let me recap once more. So we had this description of classical integrable field theories. Okay, so just focus on the two-dimensional field theories for now. So we had the x coordinate and the t coordinate. X was the space in my worksheet, t was the time. So you have a two-dimensional field theory essentially. So think of this two-dimensional field theory as a classical system. So we have some associated phase space. And these are some matrix valued functions on the space space, which means that these are some matrices whose entries can be written in terms of the fields of your theory. And they also depend on this extra auxiliary variable, which is called a spectral parameter. Now, if you can find such an R matrix, whose entries can also in principle depend on the fields of your theory and these auxiliary variables, and if this complicated looking equation is satisfied, then your system is integrable in the sense that you can find a bunch of conserved charges. So you can find some functions, these TIs, written in terms of the fields of your field theory, whose time evolution is 0, meaning that those things are conserved. So you have a lot of conserved charges in your field theory, which is, I mean, try to internalize the fact that this is an unusual situation. If in a normal field theory, you don't have a lot of conserved charges. You may have some global symmetries. But here you really have a very large family of conserved charges. Because, I mean, any coefficient of any power of u is conserved. This is very restrictive. So then we said that, okay, so we have this classical field theory, which is integrable. So how do we quantize this classical field theory? And here by quantization, we're talking about quantization in the sense of canonical quantization, basically. So what we do is, as usual, we promote functions on phase space to operators, or in the field theory sense, functions of fields to, again, operators, which we write in terms of fields. So these are those functions which we have promoted to be operators that act on the Hilbert space of your field theory. Then this whole matrix now acts on this Hilbert space transferred with an auxiliary space. And then we have said, well, then we have defined this R matrix. Basically, is that it's the identity operator and then the classical R matrix and then some other stuff that we don't know about. And again, so this promoted operator thing that came from the transfer matrix, the original transfer matrix plus H bar order corrections that we don't know about. Then we said, if we can find such expressions that satisfies this equation, then that's the same as quantizing this equation, because by expanding this in H bar and taking the limit that H bar goes to 0, we recover the original classical equation. So this is going to be our definition of an integrable quantum field theory, that you can find these matrices written in terms of the fields of your theory that satisfy this equation. Okay. Now I'm going to be more specific and talk about.
I have a
chains.
question. I have a question.
Mhm.
So can you go a little bit up when you expanded R hat?
Yes.
Yeah.
Mhm.
So classically, it's the identity operator. Is it right? Because if you expand and then take products, I mean, at h bar to the power 0 order.
Well, we also,
to...
the bracket with 1 over h bar is the classical thing.
Oh.
So we will expand these things and look at things at 1 over h bar order.
Okay. All right. Okay. Now I see it.
Because so basically, let's say you put the h bar here, right? And then, so then what it tells you is that if you take the h bar goes to 0, then this just vanishes, which is what you want, because they were built with functions on a phase space, and you want product of functions to be commutative, right?
Right. Yes.
Because this is just an ordinary product.
Right. In the classical limit, they should commute, right?
Right. In the classical limit, they should commute,
yes.
not become the personal bracket.
No.
So in the first non-trivial order, they should become the personal bracket.
Right. Okay. Thank you.
Sorry, but I have a very naive question. So whenever you define the wall sheet, right?
Yes.
So is there any dynamics in the wall sheet, or is it just so is there any dynamics, or is it just flat background, or it is
by
determined
dynamics?
by you?
I mean, I'm really just talking about ordinary 2D field theory. So when by dynamics, do you mean whether it's coupled to gravity or something?
Yes. No.
A priori, I have not put any constraint on that. I mean, so just think of this as some 2D field theory where one of the fields may be the 2D worldsheet metric, but it may also not be.
Okay.
I mean, this is very general. Okay, so now let's focus on, yes?
So I have two questions. Can you explain what is the dimension of the Hilbert space that T is acting on? Because this part is still unclear to me. The T is acting on H cross B. Right. These, yes, you said that this TU acts on a Hilbert space H and cross V. So
so the dimension
what is the dimension
H
of H? Right.
Is in general infinite. I mean, in a field theory, the Hilbert space is infinite dimensional.
Okay.
But here, I mean, we are not concerned with the technical difficulties of finding a Hilbert space. I mean, we're just saying that quantization means that you have to find a Hilbert space. Whether in practice you can do that or not, that's a different question. But we can be more explicit about the dimension of V. So V basically came from the fact that our Lax matrix was a matrix. Let's say that it's an n by n matrix. So then it acts on, let's say, C to the n. This is just a path ordered exponential of the integral of the Lax matrix. So this acts on the same vector space, C to the n. And I'm saying that let's call it V. So then this T acts, I mean, this n by n matrix acts on a column vector which has n entries. So an n-dimensional vector, and that vector is coming from this vector space V. And these entries themselves are acting on a non-trivial vector space, which is H. So V is just, let's say, C to the n.
Okay, I see the point there. And another question is that when go to a big up. So when quantization, you said that you start this monodromy matrix T and you quantize that. I'm like, why is that? I'm like, you can start with L, right? You can take that.
Oh, sure, yeah, absolutely. I mean, I'm not, so the quantization is not specific to choosing T or L. The quantization works for any function on your phase space. Any function on your phase space is going to be promoted to an operator that acts on it. In particular, also these components that appear in the monodromy matrix.
Right. I see. Thank you.
Sorry, also have a like small question. So now we
Sure.
have like infinite number of conserved charges
Yes.
because the expansion of the.
Well, yes. If you have an infinite dimensional Hilbert space, then I think that's true. There may
Which
be some
Hilbert
subtleties,
space?
but H.
H. Okay, so now, and can you have like negative powers in the expansion, negative powers of U?
Yes, we can.
Okay, so is there any difference on
Actually, so in
the-
some examples, T will only have negative powers. So I will only be negative, but that's fine.
So in general, it's an infinite series of from minus infinity to infinity, right?
Sure. Yeah. If probably
But
there's no constraint.
okay.
Yeah. Bhaiya, you said that because H is infinite dimension, so you expect infinite number of conserved charges. I mean, like, if
Yes.
even the free field theory is infinite dimensional, but we don't expect that it has infinite dimensional conserved charge, right? So what do you mean by that?
No. Yeah. So as I was saying, that in general you will not have so many conserved charges in your field theory. So these are very special field theories where you do have a lot of conserved charges, but this is not always true. In fact, most of the time this is not true.
Okay.
I mean, the point is that this equation is, I mean, it's very difficult to satisfy this equation. Most of the times you will not be able to find an R matrix and a T matrix that will satisfy this equation.
I see.
So most quantum field theories are not integrable. But if you can find such a matrix and they are written as functions of your fields, then your theory is integrable. Okay, now I will now specialize to the following case, that I will consider that my spatial direction is discrete. So in a continuous field theory, so let's say this is your origin. Okay? So this is your X, this is your T. But instead of considering this case, I will consider discrete X. So what does it mean? It means that in the spatial direction, you only have discretely many points. So you have point, and those things. Time is continuous, as it usually is, right? And yeah, so this can again be periodic. So for example, this may be identified with this if you want. Okay. So we want to apply this machinery to this picture, okay? Now, let me show you some construction. Actually, let me give an example of such a theory, because these theories are very old and well-known and very well motivated. I mean, why would you study such a theory? Because let's consider the following case. Suppose you have certain number of these things, maybe capital N of these things, okay? So you have to put some degrees of freedom at each point, right? The simplest case is that you put just 2 degrees of freedom at each point. So you say that the degrees of freedom, you can, if it's only 2, you can say that it's either up or down. So this models a simple magnet, a one-dimensional magnet. So you can think of each point as an atom in a one-dimensional crystal, and each atom has some magnetization. Either it's pointing upward or pointing downward, okay? Now, if you want to model a ferromagnet or something like that, so what does that mean? It means that there's some interaction between nearby magnets. So if they're both up, that's fine. If they're facing in opposite direction, that costs some energy and so on. So you model that by defining a Hamiltonian for the system. Let's say that the Hamiltonian, you may have already seen this kind of Hamiltonian. So there's going to be a sum over all the points. So I will refer to these points as sites. So there's going to be a sum over all sites. And then there are going to be some operators. I will tell you momentarily what these operators are. And there may be some constant here. Doesn't really matter what the constant is. Well, maybe the sign matters. But these matrices are simply matrices of the SU2 algebra. So when you model your magnets with spin up or spin down, there's an action. So you basically have a two-dimensional vector space, right? So at each point, you're assigning a C2 vector space whose basis vectors you're calling either up or down. And on C2, you have an action of SU2. And these are those SU2 matrices. So basically, they satisfy the following commutational relation. And cyclic computation of X, Y, Z. Okay. Yeah, so basically this was our first attempt at modeling ferromagnets. And what I'm going to say now is that this quantum system is integrable. But let me first talk a bit about how we see this lax formulation in this system. And this is actually much simpler than what we have been seeing so far. Basically, what we want to introduce is the following. So given any two spin sites, let me draw a picture like this, which means that, by which I mean, so here you had C2, here you had C2. So this picture represents an operator from C2, C2 to C2, C2. And this is actually going to be the R matrix. Now recall that we had some spectral parameters. So we have to introduce those spectral parameters somehow. So let me assign those spectral parameters to these vector spaces. So this R is going to depend on the difference between these spectral parameters. So what I mean by this is that we have a Hilbert space associated to our spin chain. The Hilbert space is simply a product of n copies of C2. Here you have n of these things. And are ij. This is some matrix that acts on the ith C2 and the jth C2. Okay, and so this is a map from the Hilbert space to the Hilbert space, but it only acts non-trivially on the ith and jth vector. Now, so this simply means, I mean, this is my diagrammatic way of representing this R matrix. The point of these pictorial expressions is the following. Actually, so there's a simpler version of this RTT equation that only involves the R matrices. So let me write that down. It's easy to write this in pictures. Okay. So at each line corresponds to a factor of C2, but for notational convenience, I'm going to write them as, let's say, V1, V2, V3. So V1, V2, V3. So you should read this picture from bottom to top as evolution. So you start with the tensor product of V1, V2, V3. You also end with V3, V2, V1, but the tensor product is isomorphic. So you have a map from the same vector space to the same vector space. So both pictures represent an operator like the following: V1, V2, V3 to V1, V2, V3. Okay. Now, what exactly are these operators? So here I'm going to use this diagrammatic representation of the R matrix. So I'm going to view this intersection as an R matrix. So here I have an operator that acts on V1 tensor V1, V2 and gives you something that lives in V1 tensor V2. And here you have another R matrix that acts on the image in V1 here and V3 and gives you something in V1 and V3. And you have another R matrix that does something similar, and ultimately you get a map from here to here. The same thing happens here. The only difference is that you are changing the order in which the R matrices act on different components. Okay. So, although I have not showed this thing, but it is actually easier to show than this equation, which is the fact that if you have such an R matrix and such a T matrix, this R matrix will satisfy the following equation, that these two maps are going to be identical. Okay. Now, if you write down these maps in terms of the R matrices, they kind of look weird. So for example, if you look from here to here, so the first you have some R matrix that acts on V1 and V2, right? So you have R1 that acts on 1, 2. Then you have an R matrix that acts on 1 and 3. So you have R1 and 3. Oh, by the way, so each line has an associated spectral parameter. So you can call them U1, U2, U3. So R1 will be a function of U1 minus U2 and so on. But Rij will always be a function of Ui minus Uj. So let me not clutter the notation. And finally, you have something that acts on 2 and 3. So you have R2, 3. And this equation tells you that this composition of R matrices is the same as R2, 3, and then 1, 3, and then where is this 1, 2? Okay. So this is the equation. So basically what I'm saying is that a simpler version of this equation is this equation that involves only the R matrices. But what about the monodromy matrices? I'm claiming that if you have an R matrix satisfying this equation, you can build the monodromy matrix. And let me show you how. But before I do, is it clear what these equations mean? Or are there any questions?
How do you define the ordering of these indices of R? Because
which order?
like, is it R12 or R21? How do you know that?
Oh, I mean, I'm just reading. Oh, yeah, actually, maybe I should be careful. So I should read from left to right or something like that. So let me see.
Yeah.
So here I have 1, 2. Here I have 1, 3. Here I have 2, 3, right?
3, 2, right? Left to right?
Yeah, left to right in the input. So this first and then this. So here I have 2, 3. Here I have 1, 3. And here I have 1, 2. Yeah, that's fine.
Yeah.
Yes.
Yeah. For the integrable spin chain you're considering, how you know that the Hilbert space will be just simple tensor product of some C2 spaces? I mean, aren't they interacting with each other?
Well, the Hilbert space I kind of defined by saying that at each side I have C2, and if that is the case, the Hilbert space is always going to be a product of what I have at each side, regardless of whether it's interacting or not. I mean, if it's interacting, the time evolution of states are going to be complicated, but the Hilbert space is going to be just as a product.
Okay.
Sorry, I also.
Mhm.
Okay, someone else had a question. So when you define the Hamiltonian, do you need a periodic condition
Yes.
there? Because
if your spin chain is
one.
if your spin chain is periodic, if you're identifying the first side with the last side, then you have to say that S
n+1.
the first one is the same as n+1.
But is it necessary or
no? I mean,
in
if
general,
your
how
spin
would you
chain may
define-
not be periodic. I mean, your spin chain may not be periodic. I mean, then you have to. That's what I mean. I mean, then you have to end maybe one step earlier.
Okay.
I mean, you only have terms that make sense. If there's a term that doesn't make sense, that term doesn't exist in the sum.
And don't you have any self-interacting terms?
No.
Okay.
I mean, because if you think physically, what would a self-interacting term do? It will give you a self-energy of some state, which doesn't. I mean, that may modify the total energy, but it doesn't.
But yeah,
it's not going to modify the evolution of the system.
Right. Yeah.
Okay, so given an R matrix that satisfies this equation, you can always construct a monodromy matrix in the following sense. Let these be the sites that you have in your spin chain. So V1, V2, V3, so on. They all come with a spectral parameter U1, U2, U3, and so on. Introduce an auxiliary line. Assign a vector space U with a spectral parameter Z. This picture now represents a map from your Hilbert space tensored with U to your Hilbert space tensored with U. The Hilbert space is a tensor product of these vector spaces. I have now added another auxiliary vector space. So now you have a map from the Hilbert space that lives here, which is a tensor product of these things, which is H and U. And the output lives here, which is a tensor product of these things, which is again H, and what lives here, which is U. And how you construct this map, you have an R matrix at each intersection. You take their product. Now take a trace of this. So let me call this. So my claim is that this is a monodromy matrix. Now let me argue why that is true. By the way, so this monodromy matrix will of course depend on the spectral parameter of this thing. So take the trace of this monodromy matrix, trace only in the U component. So pictorially, I'm going to represent this as looping around, meaning that, so you have some index associated to this vector space here and the same index associated to the vector space here, and you identify these indices and take the trace. That's all I mean. Now introduce yet another auxiliary line. Let's call it U prime with spectral parameter Z prime, and again take the trace. Okay, so you have T of Z prime, take trace with in U prime. Okay. So this equation is a very famous equation. It's called Young-Baxter equation. Now, I'm going to make the following claim that Young-Baxter implies So let me call this T Z and this T prime Z prime. Actually, for simplicity, I'm going to take both to be the same U so that I don't have to write T prime. But Z prime is fine. Okay, so then the claim is that T at Z commutes with T at Z prime for arbitrary values of Z and Z prime. Now, how do you prove this thing? You have to, what you can do is that, let me kind of sketch what's going on. So what you can show is that if you have this picture, then this intersection can be moved to the right of this using the Yang-Baxter equation, and you can keep doing that until it's completely on the other side. So this is equal to this. So first you show this, and then you show that if you have a trace now, so you identify this with this, and this with this, this with this, and this with this, then this picture implies that this line, this can be moved to the other side. So the ordering of these two operators can be swapped. So you can bring this here and bring this here. So using this kind of move. And that's the same as saying that these two operators commute. Okay, so now what is the benefit of these two operators commuting for any value of Z and Z prime? The benefit is simply that you can expand this equation now is Z and Z prime. And since this equation must hold for any value of Z and Z prime, let's say that your expansion is something like this. So this is a sum over I, Ti, Zi. So then by expanding this, you will find an equation that will look like Ti, Tj, Zi, Z prime J, sum over Ij equals to 0. And since this has to be true for all Z and Z prime, these coefficients commute for any I and J. And these coefficients are functions that only act on your Hilbert space. There is no auxiliary space because we have already traced over the auxiliary space. So this is similar to the classical situation where these Mondrian matrices, well, the classical situation was somewhat earlier. But so this was a classical Mondrian matrix. The entries were functions on the phase space. The whole thing was matrix valued thing, but once you take the trace, you only get a function on the phase space. So in the quantum case, when we take the trace, we only get an operator on the Hilbert space. There is no auxiliary thing. So now you have a lot of operators on a Hilbert space that all mutually commute. Okay. So now in the quantum sense, we have a lot of conserved charges that are also involution. Sorry. So you may object that this only tells you about the involution, not that they're conserved, because to be conserved, they also have to commute with Hamiltonian. So now the physical part. There exists an R matrix, a quantum R matrix, such that if you take the derivative of, well, this will sound weird, but if you take the derivative of your transfer matrix with respect to the spectral parameter and set the spectral parameter to 0, you will recover the Hilbert space. Sorry, you will recover the Hamiltonian of your spin chain. Now, this Hamiltonian is called the Hamiltonian for the XXX spin chain. This XXX suggests that the coefficients of all these three terms are the same. If you have, say, something weird here and something, let's just, you put some random constants here, then this will be called XXY. If you put all three different, then this will be called XYZ. so on. But okay, qualitatively they are the same. Yeah, so this is of course a very non-trivial claim. You have to actually find such an R matrix. The point is that you can find such an R matrix such that yeah, this equation is satisfied. So what it tells you is that this Hamiltonian is in fact a function of all these conserved charges. Since all these conserved charges mutually commute, they also commute to the Hamiltonian, and hence they are conserved charges. So this is the description of a quantum spin chain, which just simply shows you that if you have this Hamiltonian for the spin chain, you can find an R matrix that satisfies this Yang-Baxter equation. You can construct a monodromy matrix and a transfer matrix from which you get all these conserved charges. There's still the question of actually constructing the eigenstates of this Hamiltonian, right? Because when we want to solve a quantum mechanical system, so what does it usually mean? It means that you have a Hamiltonian and you want to find the eigenvalues of the Hamiltonian and the eigenstates of the Hamiltonian. So far, all we have shown is that in this quantum system, we have a lot of conserved charges. We have not said anything about what the eigenvalues of this Hamiltonian are or what the eigenstates are. Now, there is a systematic way of constructing these eigenstates, but it will take some time to describe. So what is the best way to do that? I think I have already taken up about 1 hour and 45 minutes or something like that. I can try to briefly describe how to find the eigenstates, although then I will not have time to describe how this thing relates to gauge theories. So should I try to do that very quickly, or should I try to do that at some later time?
Personally, I think you can, I mean, at least I will be more benefited if you do some later time and slowly, don't rush. But of course, it depends on your time and of course for the other ones.
I am fine with taking another day. I mean, if the organizers are okay with it, because I mean, I assume there may be other speakers who want to speak.
Maybe not for this session, but yeah, I mean, we would like to resume after Christmas as well. So
okay.
So I mean, I am always looking for speakers, so you can talk as much as you want.
Then let's defer it to another day. Okay, so before I then finish today with some concluding remarks about why this is interesting, even if we don't really care about spin chains and only care about quantum field theories, let's make sure that we kind of understand what's going on in the spin chain case. So is it clear what I mean by integrability of the spin chain, or what the spin chain is? Yeah, I mean, if you have any question about the spin chain. Mm-hmm.
Yeah, it was quite clear about spin chains. And of course, integrability also in this setting, as you have explained.
Mm-hmm. Yeah, so I mean, one question you may ask is that why did we talk about the classical system or classical R matrices, classical Lax operators? Why? I mean, the spin chain, I could have just defined the spin chain and the Yang-Baxter equation the same. The point is that in this quantum setting, it's not obvious what should be the definition of a quantum integrable spin chain, or what should be the definition of an integrable quantum mechanical system. In the classical setting, it's clear what it means to be integrable in the Liouville sense. It means that you have a certain number of conserved charges, which restricts the dynamics in your phase space to be in a half-dimensional space that can be written in a very simple way using the so-called action angle variables, right? Meaning that you can find coordinates using the conserved charges in terms of which the solutions to the equation of motion is just linear in time. So that's a very concrete definition of integrability. But then we argued that this definition is equivalent to the Lax-Square definition, that you have some matrix valued function on a phase space, and they satisfy some equation that looks like flatness of some connection. And then we further generalize it to the case that you can define something that looks like a Wilson line or a monodromy operator. And using a spectral parameter, you can get those conserved charges in involution by expanding that operator in the trace of that operator in terms of the spectral parameter. Now, notice that that final thing is what we translated in quantum mechanics. We have said that we have some Hilbert space with some Hamiltonian such that we can find an R matrix satisfying these equations that allows us to construct a monodromy matrix. And then by taking a trace, we get the transfer matrix. And then by expanding the transfer matrix in the spectral parameter, we find conserved charges. Now, if you didn't know that this has something to do with Liouville integrability, I mean, you can question why this has anything to do with integrability. You have some conserved charges in a quantum mechanical system. Great. What is so special about it? The thing that is special about it is precisely this Yang-Baxter equation, which came from some version of Liouville integrability, which is why we call the existence of this Yang-Baxter equation quantum integrability. Yeah, so if you have any question about the integrable spin chain system, please ask.
So yeah, we thank Nafiz for the beautiful talk. And if you have any question, feel free to raise your voice and mute yourself. And
So if anybody else doesn't have any questions, so can I ask a question of space? So
Yeah, of course.
You mostly talked about here like the XXX spin chain, right?
Yes.
But you can also do like, I think XXZ or whatever.
Yeah.
And I think there is a limit where the XXZ spin chain becomes like Turing model or something like that.
Yeah.
And I think you can also define these Turing models in terms of this X pair and this kind of things and prove they're integrable.
Yeah, I mean, so basically, so as I was saying that I'm going from the continuum version to the discrete version to get to the spin chain, right? But then you can consider you have many, many lines that are very close together and then go in the opposite direction. So by taking a continuum limit of the spin chain, you will get some 2D continuous quantum field theory. And as long as the construction of your monodromy matrix, this transfer matrix, and the R matrix, as long as these things do not get screwed, right? And basically what will happen? So here, the R matrix, for example, acts on two factors of Hilbert spaces. Each factor of the Hilbert space is assigned to each point, right?
Right.
So in the continuum limit, instead of having different points, you will have a continuous variable X. So your R matrix will simply depend on an extra variable X. Something like that. So you can imagine that all the constructions that we have for the spin chain will have some continuum limit. And then in the continuum limit, you will have a quantum integrable quantum field theory in 2 dimension, which will have these formulas, the thing that we talked about earlier. And yeah, so that's the Turing model that we're talking about.
I see. Okay. But I'm still not sure, like, what was the purpose of defining U that you did at the beginning? Because at the very beginning, you defined the U parameter, right?
Yeah, so here you can say that U makes the problem simpler by allowing us to expand our monodromy matrices or transfer matrices in terms of the spectral parameter. So here U is Z. And the coefficients gave us the conserved charges. So if you didn't have this extra parameter, you wouldn't be able to expand. Then you would have to take T various powers and take trace and have to call those conserved charges. That will also work in many cases. This just makes the computations easier.
Okay. So for example, if you go to the continuum limit, there you can, for example, you can have also like infinite charges, right? And
yes,
there is an interpretation of those infinite charges. For example, you can call them instantons or solitons, depending upon
that's right. Yes.
How you do stuff. But like here, what is the interpretation? This JI, this infinite conserved charges, like.
That's hard to explain.
I see.
I mean, I personally don't know what the interpretation of the higher charges are. Some of the lower charges are easier to interpret. Certain number of excitations of certain types and that kind of things.
Okay.
But the higher are, the higher order you get in Z, the more complicated these things become, and it becomes difficult to interpret them.
Okay, thank you.
Can I ask a question?
Sure.
Yeah, so I was, can you go a little bit up? Yeah, this diagram. So, so this diagram, how I see it, this is the vertical lines are the points in the chain, right?
Yes.
And when you're moving up, do you mean that it's moving in the time direction?
Yeah, we could say that. Well,
and then you're taking a section.
Sure.
And
sorry, what do you mean by taking a section?
By a section, I mean this U thing, that loop thing you wrote. I mean, I'm confused about this, understanding this diagram. So is it a slice is it a temporal slice?
Well, okay, so let me try to explain this diagram a bit more. So suppose you have this line, right? So and here you have some vector space V.
Yes.
And so you can read this diagram as the identity operator acting on V.
Yes.
Okay. So if you start with some state here, let's say some state here, you end up with the same state here.
Yes.
Okay. Now, introduce another line, assign the vector space U. Now, think of this diagram as some map that takes a state in the tensor product of U and V and gives you a state in the tensor product of U and V. Okay.
Okay.
Now, you can think of this as time evolution, but you don't have to. You can think of this as some operator acting in the same time. I mean, yeah, I mean, the main part, okay, I mean, time evolution is also an operator that acts on the Hilbert space, right? So you would write it as some operator acting here. So if you want to think of it as some kind of time evolution, that's okay. But strictly speaking, this is not a time direction, but okay, whatever. Now, is it clear to you that this diagram can represent an operator like this? Because you start with some, you put some vector here, let's say alpha and psi, you end up with something here. So psi prime, alpha prime, right?
Yeah.
Or some linear combination of such things. Now, this is the operator that I'm writing as R hat. Okay.
Oh, okay.
So now suppose I have two vertical lines and one horizontal line. So then there's an R hat here and an R hat here. So this first R hat takes some state from U tensor V1 and gives you a state in U tensor V1. And the second R hat takes, sorry, this should be V2. And the second R hat takes whatever you had in U tensor. So here you have this state in U tensor V1, right?
Right.
So this has a component in U and a component in V. So this R hat does not touch the component in V1. It takes the component in U and something coming from V2 and gives you a state in tensor product of V2 and U.
I see. Okay.
So ultimately now you have something in V1, something in V2, and something in U. So altogether you have a map from the tensor product of U tensor V1 tensor V2 to again U tensor V1 tensor V2. So this is a map from U tensor V1 tensor V2 to the same space.
Yes. But so this kind of mapping is always mapping a product state to a product state, right?
No. It can map to a linear combination of product states. But then you act on the desired components by linearity.
Sorry, can you repeat the last line again?
Yeah, so let me just say that suppose you start from alpha tensor psi 1 tensor psi 2, right?
Mm-hmm.
So the first R1 will act here.
Yes.
The first R hat will act here and give you some linear combination of things. Suppose alpha, no, maybe beta I tensor maybe chi1j with
Yes.
some coefficients. Okay.
Okay. Okay.
And nothing changes for the psi2 part.
Okay.
But the second R2 will, so you will go to each summand by linearity, and you will look at beta and psi2 and modify them according to the second R matrix. And then you will get again a sum of various things. I mean, now there will be, so here you had I and J. Now we'll have I, J, K with D, I, J, K, gamma, I, tensor. Well, it's starting to look complicated, but this is kind of the idea.
It's clear, yeah.
Mm-hmm.
So, so from the diagram, it's we cannot say anything about these coefficients, right?
No, that's hidden. You have to know what R hat actually is to know what these coefficients are.
Right.
So I'm saying the coefficients, I mean, that information is not present in the diagram. I'm simply saying that you have some matrix R hat that I am representing by this diagram.
Right.
And now, of course, you can take the trace over U, right?
Yes, you can do that.
Yeah, so that means putting another gamma here and just contracting this gamma with that gamma. So ultimately, we'll have this product of chi1 and chi2. And that I am representing diagrammatically by this picture. So there's no open end for this thing. So the only open ends you have are for V1 and V2, which is why I'm saying that this is a map from V1 tensor V2 to V1 tensor V2.
Right, yes, yes. But when you were introducing this, when you define the R matrix, it was acting on a space Rn cross Rn, right?
Yes.
And now this U and this V1 or whatever Vi take doesn't have any correlation between them.
A priori, no, right. So this is a slightly more general version of the R matrix.
Right. And do you have ideas about like quantum information, quantities like entanglement and these things from these states? Can you define those things like?
That's an interesting question. I don't know really, but I assume there should be many known things. I mean, I'm certain people have studied entanglement.
Like entanglement, entropy and stuff like that, yeah.
Sure.
Okay.
Yeah, so the main point in this diagram was that if you construct these Mondrian matrices by taking product of the R matrices, then this Yang-Dexter equation allows you to slide this operator past this other operator, which gives you, which tells you that the transfer matrices are commutative for arbitrary values of Z and Z prime.
Yeah.
Hence the existence of conserved charges. Okay, so if there are no more questions, so let me just end with the few comments about, so why would you care about spin chains? The reason is that, so we can exactly solve this spin chain, meaning that we can find the spectrum of the Hamiltonian. So in this case, this is Hamiltonian. We can exactly find what the eigenvalues of these Hamiltonians are, and we can construct the eigenstates. Now, that's, of course, very nice for the spin chain system. But the point is that there are many gauge theories where if you look at certain subsectors of the gauge theories, meaning that you don't consider all the operators in a gauge theory, but only certain operators in a gauge theory, then there's a one-to-one mapping between those operators and the eigenstates of this spin chain. And knowing the solution of the spin chain, meaning that you know what the eigenstates here are, you can compute the overlaps of those eigenstates. You can compute the correlation functions of those certain operators in gauge theories, simply from this one-to-one correspondence with the spin chain. Now, this is very powerful because normally in a gauge theory, you don't expect to be able to compute much. Exactly. I mean, you can do some things in perturbation theory. But this tells you that in those gauge theories where there's a one-to-one mapping between certain operators of that gauge theory and the eigenstates of this Hamiltonian, you can compute whatever you want with those operators by mapping the problem to spin chain and computing that thing in the spin chain. So this then becomes a very powerful tool for computation in gauge theories. That is why we care about spin chains. And these mappings between spin chains and gauge theories is fascinating. So hopefully I will talk about it another day.
Maybe last question from me. So you talked about gauge theory mapping and also give some nice example using kind of scalar theory. So what about spinors? Can you also do this sort of thing with the spinors?
So the gauge theories that I mentioned, they will have spinors, but the operators that I will talk about, I mean, the operators that we know correspond to eigenstates of these integrable Hamiltonians, they are all bosonic.
Yeah, maybe not those operators. Say, for instance, I take just a spinor field. Say, for instance, Dirac field, and now combination of Dirac field is a bosonic.
Yes.
So the parabola is still bosonic, but the fields are fermionic. So in this, can you use some variant of this machinery?
So Ronyan, I didn't get your question. What? Can you repeat?
So maybe I rephrase a bit differently. So as far as I have understood, what you are doing is solving some partial differential equation which satisfies certain condition. That's umbrella of this integrability classical quantum, depending on context. And if certain condition are satisfied, then you can solve things explicitly. You can write the solution. Okay, so then from PDE point of view, whether we are considering a scalar field or gauge field or spinor field depends on what sort of differential operator you are considering or what sort of observable you are considering, right? That's how what enters. So that's why I was wondering if I consider, say for instance, Dirac field. I know that this is not integrable, but just for instance, some version of Dirac field. And now I can construct observable, which are bosonic out of fermionic, like bilinears. So, and then can you apply some variant of these ideas for a Dirac field?
So I know some example that does involve both bosonic and fermionic fields in which there is some mapping between spin chains and those gauge theories.
Okay.
But the theories themselves are somewhat complicated, and the spin chains will also have I didn't talk a lot about symmetries, but for example, the spin chain has an SU2 symmetry, right? Because these are written in terms of SU2 generators, and this is basically the Casimir operator of SU2. So this will commute with your SU2. So you have an SU2 symmetry in the spin chain. But those theories that I just mentioned that have fermions and still dual to spin chains, those spin chains will have symmetries, say, well, maybe as L/M/N. So they will have super Lie algebra symmetries.
I see.
But there are certain examples of that.
Okay, then maybe also a complementary thing. So you give this example using discretization, like some lattice model. So is it true if one can show that certain lattice model is integrable in some certain sense, then the continuum limit, if exists, is also integrable?
That's a good question. I don't know if that has a definitive answer. In some cases, we know that it's true. I don't know if it's always true.
Okay, yeah. So
for example, Onion Bhai, if you take the exact Z model, okay, and the continuum version of it becomes Thirring model at some point, and that's integrable as well.
Yeah, so that's an example where it works.
Yeah, I mean, usually for 2D, this is in a better situation, but if you go to higher dimension, then things usually get worse.
So for example, there are a higher version of this thing. I mean, so here a space is discrete but one-dimensional, but you can also have discrete but two-dimensional.
Okay, so it's kind of like 2+1 Heisenberg model, right?
Right.
Okay.
Those are also very interesting things, and of course, sometimes they also have continuum limits, and those field theories are also interesting. But it's already difficult in one dimension. It gets more difficult in higher dimension.
It's very complicated.
Nafiz Bhai, just one thing, like these spin chains, like so what about the conformal symmetry? Like, are they in the CFT or not, or what is the situation?
Which conformal symmetry?
So is there any, like, usually, when you go to the continuum limits, they, they have they're usually in the CFT, right? Because they're in the 2D, right?
Sometimes, yes. Well, I don't know if that always has to be true, but
I see. So spin
not-
change doesn't
not
have to
all
do
2D
anything with that in particular, right?
No, of course
Well-
not all 2D quantum field theory are conformal.
No, I know. Yeah.
right. But if you can find some 2D integrable conformal field theory, I mean, so in this spin chain, you had a lot of concept charges, and in the continuum limit, they will become concept charges of the field theory, right? So it's not too hard to imagine that some of the charges will fall into the coefficients of the stress tensor.
Right.
That's how you will get conformal symmetry.
Okay.
But what are the constraints that you give on the discrete case that gives you a conformal symmetry in the continuous case?
No, I mean, there's no obvious constraints that will
Right.
become conformal.
Okay.
Okay, so if there are no further questions, at least we thank Nafiz for this beautiful talk and a beautiful discussion. And we hope to hear more from you. So the next talk will be again after 2 weeks by Milan Bhai on classical general relativity.